Hi everyone, this is my special lecture series of Linux programming under my channel Adept to Teach. Myself, Dr. Ramandeep Kaur. I'll be covering the following contents in my lecture.
Okay, so in the previous lecture, we discussed about the structure of your Ext2 file system, wherein we discussed that you have different partitions in your hard disk drive, and every partition has got the first block as your boot block, where your information pertaining to the booting of the system, which files to be picked up from where, how to check the peripheral devices, from where to get the secondary, where to get the image of your operating system from secondary storage to primary storage to RAM, how it has to be done, what are the background processes and daemons that have to be started. So that information is stored by your boot block. The second is starting from your block groups. Now every partition has different block groups, wherein the block groups represent the collection of your entire data. For example, let's say you have uh, C, D, E partition. Let's say we are talking about partition number D. Now in partition D, let's say the address of the partition D starts from 1000 to let's say 2000. So we have made block groups of let's say 100 each. So there will be 1000 block groups in address space 100, 1000 to 2000. So every 100 space is represented by one block group. That's what we meant by block groups. So when we say what are our block groups, then we will think about our D partition, wherein our D partition, I said, let's say starts from 1000 and it goes, let's say, up to 1999. That means 1000 partitions. Now let's say this is my partition and this is let's say my D partition. So here let's say I have different groups that I have created and every group is of size 100. So this is called my block group 0. This will be my block group 1, block group 2 and block group 3. Now every block group will in return comprise of this entire structure. So every block group will have a super block, will have group descriptors, will have data block bitmap, will have inode bitmap, inode table and actual data blocks. So this 100, the first partition which is of size 100, this will comprises the first block in that. That means 101 block will comprise of super block. 102 block number will comprise of the group descriptors. Then 103 data block bitmap, 104 inode bitmap, 105 inode table, 106 to 199 will be available as data blocks for actually storing the data. So initial blocks will be reserved for storing these 5 things, and rest of the things in every block group will be reserved for your actual data storage. So whatever data you would be storing, whatever actual files you would be storing, that will be only available from block number 106 to block number 199. Likewise, when you go to second block group, again it starts from 200. So 200th location is for super block, 201 for group descriptor, then so on. And from 206 onwards, you will have your actual data blocks. So this partition, this block groups is made. For example, let's say if it was not there, then right in the first block you were only storing this information up till this part. Rest of the blocks from 106 to 1999 were available for data blocks. Now, what data is stored at where location, which location, the pointers that are stored. Every time you would have to go back, you will have to start searching again, and you have to keep on pointing. Now, every time you have to point a lot chunk of record. 1000 records you have to search through for a particular file. This will be very much time consuming. In order to understand, in order to speed up your file searching or work modification of the file or creation of the file, smaller blocks have been divided. So one type of data is stored in similar type of block. Like whatever files, let's say I'm storing a Linux file. The size of Linux file is greater than one block size. So that will be stored in the location from 100 to 200 only. Similar types of files are stored in similar block. Then let's say video. Then video files would be stored in similar types of block. So whenever you are searching for any particular record, you will go directly to that block. You will look at the table, which file is at what location. You will directly go to that file and you will search. Now let's reference it with the help of a library. You go into a library. In your library, you have different almirahs that are kept. Every almirah has a sticker on it which tells you that which books are put here. Then every section in that almirah also comprises of the number of books, the different categories of books. Now, if you have to identify a book of MCA 5, then you will go into the library. You will not search for all the almirahs and all the sections in the almirahs. You will directly locate which almirah is kept for MCA 5. Then which section comprises of the books of Linux. So from that section, you will go to almirah. From the almirah, you will go to a particular cabinet in the almirah and you will pick out the book. Now, this is what we are doing here in your block groups. We have made some sections. Every section has a reference number. You just see the reference number, which file you want to identify, which is the type of the file. Go to the exact location of the file and read that file. That's what we are doing in different types of block groups. Now, let's see what is the exact structure and what exact details are stored by every category. Now, first we said in every block group you have a super block. Now, this is a redundant block because you saw that it is in one partition, then it will be replicated in other partition. The same structure is there in all the partitions. So, in first partition you see a segment of 5 things. In the second partition, again the segment of 5 things, wherein first 2 things are repeated. That first group 2 things are first your super block and second is your block group descriptors. Now we'll come to the detail of what the super block is storing, what is the block group descriptor that it is storing. The reason why these two are repeated is if there is a crash in your file system, there is a corruption in your file system and one partition gets let's say disrupted, then you will go to the second partition. You will find the you will go to the second block group. From there you will find the next super block details. You will get the file group descriptors. Now these two stores the details of all the block groups that are available. So if your system fails, you can go here, you can recover your system back. This is why these two things are replicated in all the groups. Another thing, that whenever the system starts reading, it goes to block group 0. The super block and block group descriptors from block group 0 are only read. When it goes to block group 1, it will not read these two things again. It already has a copy in the memory. So it will not read these two things again. This is only kept for emergency purposes. So it will not read it again. It will directly go to the next block bitmap and inode bitmap and inode table. So super block and block group is created for all the groups and all the partitions in one go. This will be replicated everywhere. Now next is okay, the work of the block group is it will contain the entire information, different blocks. What are these storing? The bitmap information and what information is stored about every file. This is what the block group descriptor is storing. That means what are the number of groups, what blocks are available, what inodes are available. This entire information your block group descriptor will store. Then next is your block bitmap. What it will do is it will store 1 bit per block. What it is doing, that let's say we are considering the sample of 100 to 199. This is one block under first partition. Now in this block group, let's say there are different parts. There are different again spaces. That means 101, 102, 103. Now, whether a block is storing an information or not, that is what a bitmap is stored. If this is containing any information, then bitmap will store the details about, let's say, at 100th location, the data is stored. So, bit stored is 1. At 101 location, it's empty, so bit stored is 0. So, bitmap stores detail of every block in the block group, and if it is occupied, then it will store it as 1. If it is not occupied, it will store it as 0. Since bits are only two, either 0 or 1. So 0 represents that it is vacant, 1 represents that it is still it is occupying some data. This is how we are storing the bitmap. So this type of bitmap is stored for your block bitmap. Similarly, this type of bitmap is stored for your inode bitmap also. That means if what inode numbers are free, there is no file at that particular inode number, and what inode numbers still have some files which are allocated to it. So we have a block bitmap, we have a inode bitmap, then we have a inode table which will comprise of the list of all the inodes that are available and some important information like the access rights of every file, to which the owner of every file, the group owner of every file, and special permissions of every file, the file name. This information will be stored in your respective inode table. Now let's see what is the information that every super block is comprising of. Now, super block comprises of the block group number. That means currently the super block of which block group is read. I said right in the beginning block group 0 is read. So it will store that when you are reading the block group 0, this block group 0, this super block is of which block group. This is important. Why? If let's say there was some failure in block group 0, which means now block group 1 is read. So if the super block from block group 0 could not be retained, then it has to go to block group 1. Now the super block, whether it should be read from block group 1 or not, because by default setting is that only super block from block group 0 will be read, from the first block will be read. From after block group 0, it will not be read again. Super block and block group descriptors, it will not be read again until there is a problem of some system crashing or some failure. So if the super block from block group 0 was not read, that means your block group 0 was not available, then it has to move to next group. So the system should know the super block whether I have to read or not. And now since I am reading the super block, from which group I am reading it. So it will store the information 1. That means 0 block group, there was a failure. First I have to retain the information. I have to I have to recover my system back. I will retain all the information. Then I will start reading the information further. This information is very important. When we will see the how the booting is done, then you will understand why we stored this information. So this information is important, that from which block this super block is read. If it is a default block, that means if you are reading from 0 block, then it will mark it as 0 block number. If it is marking as 1 block number, that means 0 has failed, there was a crash in block group 0, the system has to recover. So super block from your block number 1 has to be read, the system has to be recovered. So this sector, this system is recovered, the file system is recovered, and then you can go on with further reading all the important information of the system. The second thing is block size. Now, when a file system is loaded, in any partition, the sizes of every block is fixed. So what block size is fixed for the entire partition, that block size is retained. Because maybe in partition number 2, you implemented Ext2. In partition number 3, you implemented Ext3. So in partition number 2, you said the block size would be maximum 4 KB. In Ext3, you said the block size would be maximum 16 KB. So it has to understand that which is the block size, because depending upon the block size, the files will be allocated, whether at what size the single direct pointers or the single indirect pointers, they have to be started in. So after 4 KB, if the file size increases, then 5th KB has to be stored in single indirect pointer. Likewise, in the case of Ext3, if you set the block size as 16, then up till 16 bytes, the file will be stored. If the file is of size greater than 16 KB, then it will be stored to the next single indirect pointer. This is why this information is very important. Next information is how many number of blocks per group. Again, the second you fix the size of the block, the number also get fixed. If you say the size of every block will be 4 KB and you have totally, let's say, 16 KB of size, then that means you have 4 blocks. So how many number of blocks per group and what is the size of every block? Next is how many number of free blocks that are available in the file system, how many number of inodes that are available in the file system, and what is the first inode storing. So if whatever type of file system you are using, the first inode number is reserved for your root. That means it stores the location of your file system. So inode number 001 is reserved for reference of your file system. So the first inode number stores the information about your root directory. Next, let's see how the group descriptor looks. Now for every group, I said you have a super block and you have a group descriptor. This part will be repeated in all the groups and all the partition. This is fixed right in the beginning. So this will have the information of all the blocks, all the groups, all the inodes, entire data, entire method of storing about all the partitions will be contained in this super block. Now this block descriptor, what it is comprising of? Let's say it goes to first block group 0 from where it is read. So it will have the information of block group 0. Under block group 0, it will further have the information of this block group 0, what is the bitmap of this block group, what is the inode bitmap and the reference to the inode table. So this block descriptor table will have a table like this, wherein the first index will be block group 0. This will redirect to the block bitmap and inode bitmap and inode table of block group 0. Now next would be your likewise second block group. So group number 2, block group 2, the super block and super group descriptor, they are same, they are constant. I said they are storing the information of all the groups. So see, even if it is read from group number 0, it is still storing information of all the other groups also. So again in group number 1, the next index is 001, group number 1. Then again the information of block bitmap of group 1, inode bitmap of group 1 and inode table of group 1. Likewise, whatever are the number of block groups, all the information are stored in this group block descriptor. Now, what is information exactly is stored in this group descriptor? It says it is storing information about all the groups that are available, and for every group, it will store an independent block bitmap, inode bitmap, and inode table. Together, when information of all the groups are added, it is stored in a table. It becomes your group block descriptor. Now, how the bitmaps work? Now, like I said, a bitmap stores information either 0 or 1. So, every bit represents, 0 bit represents it is vacant, 1 bit represents that it is still occupying some space. Now, let's say you have this block bitmap. Now, every location is comprising of some bits starting from 0 to 1. So, byte number 1 is storing information, byte number 2 is storing information up till 1024. Now, by default, your block, super block and block group descriptor, they start in your memory from location number 1024. That means if this is your main memory, or let's say this is your main memory, then from location number 0 up till location number 1023, This will store up till location number 1023. This will have your information with respect to your booting. After this, that means from byte number 1024, this is your 1024 byte number. From this, your super block and your block group descriptor will start. Okay, so every block will be of size 1024. So this is a fixed size. Every block is of 1024 bytes. So the size of every block is 1024 bytes. The address spaces that are available are also 1024 address spaces. Okay, so in every section, in every group, how the bitmap is stored. Let's say B0 represents block number 0, B1 block 1, B2 block 2, and so on. Now block 1 is is referencing to location number 1 of your actual disk block. So this information is stored at your kernel level. This information is what mapping to which location is stored at your kernel level. So block number 0 is storing information, is pointing to the actual address number 1 in your secondary storage space. This is your secondary storage space. This is your virtual mapping that is going on. This information is with kernel. This information is basically your physical system. This is your kernel view. So kernel stores this information that if a particular file has to be identified, it will identify its block number. This block number stores file at location number 1 of the secondary storage space. So whether this is occupying a data or not, it will create an information that B0 is pointing to number 1 and it is storing no information. If it is not storing information, the bit is 0. Likewise, let's say block number 1 is referencing to address number 2 and is, let's say, storing some data. So the value becomes 1 here. This mapping is very important. So bitmap says a map of all the bits, whether a particular block is occupying some bits or a particular block is empty. Entire map is storing information with respect to the bits only in the form of 0, 1, 0, 1, 0, 1. So block 1, let's say 0. Block 2, let's say 1. Block 3, let's say 0. This type of information is maintained by block bitmap. Likewise, similar type of information is maintained by our inode bitmap also, which stores information that which inode number is free, which inode number is available. So it will store information like inode 0. I said this is for file number, this is for your files. This will always occupy your root directory. So it will always represent a value 1. So inode number 1, let's say this value is also occupying some files. So again, let's say 1. Inode 2, let's say this file is free. So this bitmap will be made like this. This will be your inode bitmap. This is your, this example that I have shown, this is your block bitmap. So these bitmaps are stored in every block groups of every partition. बट दिस बिटमैप रेफर्स टू ओनली दैट पर्टिकुलर ब्लॉक. अब ये कॉमन नहीं है. बिटमैप, आइनोड मैप और आइनोड टेबल उस ग्रुप की इंफॉर्मेशन रखेगा खाली, बाकी ग्रुप्स की इंफॉर्मेशन नहीं रखेगा. उसको सिर्फ ये मतलब है कि मेरे ग्रुप में कौन सी लोकेशन पे कौन सी फाइल है भी या नहीं है, डेटा है भी कि नहीं है, ब्लॉक खाली है या ब्लॉक फिल्ड है. अगर ये सारे ब्लॉक ग्रुप्स की इंफॉर्मेशन स्टोर करना शुरू कर दे तो फिर से ये सारा आपके पास सोचो सर्चिंग टाइम कितना ज्यादा बन जाएगा. अगर मैं आपको बोलूं कि सारी इंफॉर्मेशन लाइब्रेरी की, पहले एक बार एक काम करो, एक जर्नल में जाओ, एक मैं आपको जर्नल लेजर बनाकर दूंगी, उसमें खोलो, उसमें पहले सारी इंफॉर्मेशन चेक करो, उससे लोकेट करो आपके कौन से सेक्शन की, कौन सी अलमीरा की, कौन सा आपको पार्टीशन पिक करना है. देन इट विल बी वेरी टाइम कंज्यूमिंग. रादर देन इट इज बेटर फॉर मी कि मैं पहले से ही बता दूं ये सेक्शन यूजी है, ये सेक्शन पीजी है, ये सेक्शन एमसीए 1 है, ये एमसीए 2 है, एमसीए 5 एंड एमसीए 6. नाउ यू जस्ट हैव टू फोकस ऑन एमसीए 5. अब एमसीए 5 में आप जब चले गए तो आपको सिर्फ ये मतलब है एमसीए 5 की जो सेट ऑफ सेक्शन है उसमें कितनी अलमीराज है, और कौन कौन से सब्जेक्ट को रिप्रेजेंट कर रही है। नाउ इट इज इजियर फॉर यू टू आइडेंटिफाई रादर देन कि मैं सारा का सारा आपको पार्टीशन का स्ट्रक्चर दे दूं और बोलूं लो एक से लेके एंड तक ढूंढना शुरू कर दो। This is why we maintain separate bitmap for block, separate bitmap for inode and separate inode table for every group. ये तीन चीजें हर ग्रुप में चेंज होंगी, रेप्लिकेट नहीं होंगी। सिर्फ दो चीजें रेप्लिकेट हो रही हैं, सुपर ब्लॉक की इंफॉर्मेशन और ब्लॉक ग्रुप डिस्क्रिप्टर की इंफॉर्मेशन। एक बार ये जीरो लोकेशन से पढ़ लिया तो अलग अलग ब्लॉक ग्रुप्स में ये दोबारा रेड नहीं होगा, ये पूरे सिस्टम की डिटेल रखता है। पर जो ब्लॉक ग्रुप बिटमैप है और जो आपका आइनोड बिटमैप है और जो आइनोड टेबल है वो हर एक पर्टिकुलर ग्रुप के लिए डिफरेंट है। नाउ कमिंग टू आवर inode table. Now this inode table is basically your 128 bytes in size, and for every file or directory a unique inode number is identified. Now it treats the directory, the devices, media, everything as file. So whether it is actually a file or a directory or a media or a movie or a audio, it everything will be treated as a file. So for everything you are storing in your Linux system, then uh, everything would be treated as a file, and every file will have a unique inode number. And what information we store in that file, we have already seen that when we did the inode structure. So what metadata is stored about a file? The name of the file, the type of the file, the owner, who is the permission, what are the permissions, and to watch what block group it is a part of.
Thanks for watching. If you like my channel, then kindly subscribe and press the bell button for receiving the updates.